Hello everyone, welcome to the Makri Virtual. Hope you are doing good. Today I'm going to continue with your chapter number 8, that is exceptional control flow. Hello. Yeah, I'm going to continue with your chapter number 8, that is exceptional control flow. So till now we have discussed two topics, or only one topic, that is what is exceptions and what are the types of exceptions. Now I'm going to continue with your again classes of the exceptions and next topic, that is your process. So let's start with what are the classes of the exception, means what are the types of the exceptions. Let's say exceptions may be divided or can be divided into four classes. So that is the exception is divided into four classes: interrupt, traps, faults, and aborts. So these are the topics that we will cover in the today's class. But before that, let's take a quick review what we have covered in the last class. That is the quick revision of the previous session, that is the last section or last session. In the last class, we have started with the chapter number 8, that is Exceptional Control Flow, ECF. And we have also talked about what are the topics that will be covered in this chapter. That is overview of the chapter. That is what are the topics covered in this chapter. Then we have covered what is a control flow, that is how flow will be maintained or how we can control the flow, that is known as the control flow. In this we have studied that is from the starting to the ending up, that is from the startup to the shutdown, a CPU simply reads and executes a sequence of instructions one at a time. That is CPU, Central Processing Unit, simply reads and executes the instructions. Simply read means it reads the data, and executes means interpret a sequence of instructions one at a time. So this sequence is the system physical control flow. That is a flow of the control. We can flow or the flow of the control means the time we are starting the system and the time we are shutting down the system, that is in between that time, that is sequence is known as the control flow or the flow of the control. So this is the example that we have discussed. It starts with the startup, then there is an instruction 1, instruction 2, instruction 3, instruction n, and at last there is a shutdown. So this is the time that starts from the startup and ends with the shutdown procedures. Then we also discuss how to alter the control flow. We have discussed two mechanisms that is used to alter the control flow. That is, you are either use the jump and the branch, or either use the call and the return using the stack discipline, using the stack pointer. So we have studied about the how to alter the control flow by using the mechanism, by using two mechanisms, that is either use the jump and the branch, and either use the call and the return using the stack pointers. Then we also discussed that it is insufficient for the useful system. That is, altering is very difficult. That is insufficient for a useful system. Why it is very difficult? Because the whole system will be rebooted again, will be cope up with the new changes again. So it is very difficult for the CPU to react to the changes in the system state. Why? Because the data arrives from the disk or a network adapter, Instruction divides by 0. So these are the difficulties that is available to the, or that is approaches to the CPU for the changes. Then next point says system needs mechanism for the exception control flow. So system needs a requirement so that it can alter the control flow. That mechanism is known as the ECF, that is exceptional control flow. So this is the exception control flow. This is a mechanism for the exception control flow exists at the all the levels of a computer system. We studied that this is a mechanism to control the flow, or to control the flow that exists at all the levels of a computer system. That is, at every need of the computer system we need a ECF, that is exceptional control flow. So we have studied about the low level mechanism as well as the high level mechanism. Then we also discuss about the different errors that is available, like runtime error, syntax error, and logic error. So these are the errors that we have studied, that what is a runtime error, what is a syntax error, and what is a logic error. So these are the three errors that is available, or that is encountered by using the program while writing the C program or any programming language coding is written. So these are the three errors that is available that we have studied in the last class. Syntax error is simply means the error that arrives whenever we are not using the rules of the language. Suppose C language uses a rule that for writing purpose it uses printf. If I'm not using the printf statement, that is a syntax error. In the same way, runtime error are the error that is available while the program is running, or while the program is run in the running condition. Then logic error that occurs when a program does not perform the way it can or it was intended to. That is, if the output is not applicable as per the input, so that is a logical error. That is, program does not perform the way how it will be expected. And then we have studied about the examples of the runtime error. These are the examples of the runtime errors. Then next one we have discussed, that is how to catch the runtime error. So first of all, we will try the runtime error, then we can catch the runtime error. So there are multiple blocks like try, catch. So first of all, there is a try block that is trying the or passing the error, then catch the error for execution, for resolving the error, or for simplify the error. Then we also discuss about the exception classes. That is, what are the classes of the exceptions, or what are the categories of the exceptions. That is object, throwable, error, class not found exception, input output exceptions, AWT exceptions, runtime exceptions, several more classes. So these are the different exceptions that is available, or that is stored in the exception. Then we also discuss another class, that is your error, or we have studied about the different types of error, that is a linkage error, virtual machine error, AWT error, and several more classes that is available for the error. So we have studied about different types of error in a diagrammatical representation. This is the system error, as I told you, that are thrown by the JMV or JVM, that is Java Virtual Machine, and represented in the error class. The error class describes internal system error. Such errors rarely occur. Then we also discuss about the different error, that is exception describes the error caused by your program. These are the runtime errors. Then we also discuss about the checked exception versus the unchecked exception. That is, what is the checked exception that is already checked, but one is unchecked exception that cannot be checked. So the runtime errors, or the simple error and their classes, subclasses mean their parts, are known as the unchecked error that cannot be checked, that cannot be rectified. That is known as the runtime exceptions. All other exceptions are known as the checked exceptions. So means rest of the exceptions are known as the checked exceptions, meaning that the compiler forces the programmer to check and deal with the exceptions. Then we also studied about the unchecked exceptions. That is, what is the unchecked exceptions that reflects a programming logic error that are not recoverable. Then we have discussed about the examples of the unchecked exceptions. That is null pointer exception and the index after bound exception. This is an unchecked exception. This is a diagrammatical representation we have studied. Then we have also talked about the methods, how to declare, how to draw, and how to cache the exceptions. That is how to declare the exceptions, how to throw the exceptions, and how to cache the exceptions. So this is used for the declare. This is the declare exception, that is throws exception. This is used to throw the exception, that is when we are using the function, that is the throw exception. And when we are catching or when we are using the catch block, that is the catch expression or exception. These are the three methods that we have studied. One is declare, one is throw, and one is catch. We also discuss about different method, that is how to declare the exception. That is what are the method that is used to declare the exceptions. That is used by using the syntax, that is public void my method throws IO, that is input output exceptions. Then we also discuss how to throw the exception and what is the syntax that is used to throw the exception. That is throw new the exception. Then we also discussed that exception in a diagrammatical representation. That is what is the exception? It is the transfer of the control to the operating system in response to the event. That is, if there is some event occur, so it is the transfer of the control to the operating system. So this diagram shows the exception. That is, first of all, there is an event, then there is a current, there is a next. There is a user process, this is a user process, this is the operating system, that is your OS part. Then next is your exception processing by the exception handler. That is, the exception handler is handling the exceptions, that is the exception. Then exception return, that is returned by the exception processing. So first of all, exception came. This is the arrow that shows the exception came. Then exception processing is done by the exception handler. Then exception is returned back to the user process. That is the exception. So we have discussed about the interrupt vector exceptions. We have also discussed about the asynchronous exception, that is known as the interrupt. That is why interrupt, or what is the interrupt, and when do the interrupt occurs. Then we also discuss about the synchronous exceptions. That is, what is the synchronous exceptions? One is asynchronous exceptions, one is synchronous exceptions. That is caused by the event that occurs as a result of the executing an instruction. So these are the events, or these are the event that occurs as a result of the executing the instruction, and that includes various parts like traps, faults, and the aborts. Then we also discuss about the examples of the traps, fault example. So this is what we have covered in the last class. Now, today I'm going to start with your new topic, next topic, that is your classes of the exception. That is categories of. This says exceptions can be divided into 4 classes. One is interrupt, one is trap, one is fault, and one is abort. The table in figure 4 summarizes the attribute of these classes. So these are the attribute. As I told you, interrupts are known as the asynchronous exception. Trap is known as the synchronous. Fault is also known as the synchronous. And abort is also known as the synchronous. Now, what is a cause? That is, these are the classes, these are the categories. And what are the causes of these exceptions? That is why these exceptions occur. So, first of all, interrupt. There is an interrupt. That is an interrupt. When interrupt occur, whenever there is a signal from the input-output device. So whenever there is a signal, there is a line that is going from the input-output device, that is known as the interrupt. And that is of asynchronous form. The return behavior is that it is always returned to the next instruction. That is, it is always returned to the next instruction. That is your interrupt. Then next is your trap, that is the intentional exception. Intentional exception means that is intentionally intentionally transfer the control or mechanism to transfer the control so that exception occurs. So one is your unintentionally, one is your intentionally. This is the intention one, that is your trap. Then trap is also a category of the synchronous exception. Then next is your fault, that is what is a fault? That is used to potentially recoverable error, that is used to relocate the error, that is used to potentially recover the error, that is a fault. Or whenever there is a fault, that is used to recover the errors. Then next is what we have studied is abort, that is not non-recoverable error, that is we cannot recover the, or we are not able to recover the abort function. Then this is also a category of the synchronous exception. Then there is the return behavior. It never returns. Fault might returns, but the abort never returns. So let's start with the one by one category, that is what is the interrupt, what is a trap, what is a fault, and what is a abort. So let's start with these categories. First of all, interrupt. Interrupt occurs asynchronously. As I told you, it occurs asynchronously as a result of the signals from the input-output devices that are attached to the or external to the processor. So that is a processor, or that are the interrupts that are asynchronous in nature, and that arises as a result of the signal from the input-output devices that are external to the processor. So whenever there is a signal going from the input devices and the output devices that are external devices, so as a result of the signal, or as a result of the signal, when these devices are communicating with the signal, that is known as the interrupt. There are two categories of interrupt, software interrupt as well as the hardware interrupt. This is hardware interrupts are asynchronous in the sense that they are not caused by the execution of any particular instruction. Why they are not caused by the execution? Because they are not related to any part of the instruction. They are only used for the behavior of the instruction. Exception handler for hardware interrupt are often known as the interrupt handler. So one is your exception handler that accepts the instruction and executes the instruction. That is the exception handlers for the hardware interrupts are often known as the interrupt handler. Figure 5 summarizes the processing for the interrupt. So this is a figure that shows how interrupt occur and how processing of the interrupt takes place. These are the classes of the exceptions. One is your asynchronous exception that occurs as a result of the event in input-output devices that are external to the processor. And synchronous exception occur as a direct result of executing an instruction. This line shows the difference between the synchronous and the asynchronous. Asynchronous occurs as a result of the event in input-output devices. That is, if an event occurs that gives the result in the form of input-output devices that are external to the processor. One is that is a direct result of the executing the instruction. So one is indirect, that is asynchronous. One is direct, that is synchronous. This diagram shows the interrupt, that is your interrupt handling. The interrupt handler returns control to the next instruction in the application program control flow. So this control, or this returns the control to the next instruction, to the next going instruction in the application programming control flow. So first one, this says interrupt pin goes high during execution of the current instruction. That is, the interrupt pin goes high, that is the interrupt level goes high during the execution of the current instruction. And there are the two categories, that is I current, that is instruction current or the current instruction. One is next instruction. Same way, control passes to the handler after current instruction finishes. That is, if the current instruction finishes, then control passes to the next instruction. That is your, suppose I'm using the 5 instruction and my current instruction is the second instruction. Then automatically control passes to the next instruction, that is your 5th instruction. Now interrupt handler runs. That is the duty of the interrupt handler to handle the interrupt. That is the interrupt handler. Then next point says handler returns to the next instructions. That is whenever the interrupt handler handle the interrupt, then handler returns to the next instruction. That is the interrupt is over, the execution is over, then handler returns the main point or the position or the cursor to the next instruction. This says after the current instruction finishes executing, the processor notices that the interrupt pin has gone high, reads the exception number from the system bus and then call the appropriate interrupt handler. So this is the example that shows how to call the exception control flow. Then next point says when the handler returns, it returns the control to the next instruction. That is the instruction that would be or that is available or that would be have followed the current instruction in the control flow have had the interrupt node occur. The effect is that the program continues executing as through the interrupt has never happened. Then the remaining classes of the exception, that is trap flow, occurs synchronously, that is as a result of executing the current instruction. So this is the interrupt only that is in asynchronous form that takes the result indirectly. All the other ones, that is your trap, system call, all the others are the categories of the synchronous in which the result is a direct one. So next is your traps. Traps are intentional exception that occurs as a result of executing an instruction. Intentional means that is intentional. Next is your trap, that is your unintentional, that is your intentional exception that occurs as a result of executing an instruction. So this is one of the category of the intentional exception that occurs intentionally and that occurs as a result of the executing an instruction. Like interrupt handler, trap handler also return the control flow or also return the control to the next instruction. So it passes the control to the next instruction. Then the most important use of the trap is to provide a procedure-like interface between the user and the program and the kernel known as the system call. So that provides an interface between the user program and the kernel that is known as the system call. So traps are intentional exceptions that occurs as a result of executing an instruction. So whenever we execute an instruction, these are the intentional exceptions that arise while using the instruction. Like interrupt handler, trap handler also returns the control to the next instruction. So this is the handler that returns the control to the next instruction. The most important use of the trap is to provide a procedure-like interface between the user program and the kernel known as the system call. So the important concept of or the important use of the trap is to provide an interface that is known as the system call. User program often need to request the services from the kernel such as reading a file, that is a read operation, creating a new process that is done by the for, loading a new program that is executable VE, or terminating the current instruction that is your exit. So VR or user program often need to request the services from the kernel such as reading a file, creating a new process, loading a new program, terminating the current process. That is either using the read, fork, execute, that is exeve, or exit the command. To allow the control access to such kernel devices, processor provides a special function that is a syscall. This is a special function or the special instruction that the user program can execute when they want to request the service that is the end service. This is the diagram or figure 6 summarizes the processing for a system call. That is how system call operates or how interrupt handler accepts or handles the interrupt. So first of all, there is an application that makes a system call. Then there is a system that is a system syscall, and then there is a next instruction. Here, this is the first point that makes a system call. Then control passes to the interrupt or control passes to the interrupt handler. That is your trap handler. Then trap handler runs. then it returns the handler return to the instruction that is following the system call, that is use the system call instruction. Then next is your fault handling, and that depending on whether the fault can be repaired or not. This is the fault handling. Now, next part is a fault that occurs from the error condition that a handler might be able to correct. It might be, not for sure it will be able to correct, but it might be able to correct. When a fault occurs, the processor transfer control to the fault handler. So these are the same. You see interrupt, you have seen system call. So whenever there is a fault occur, whenever there is a problem occur, so that passes the control, or the processor transfers the control to the fault handler. Then if the handler is able to correct the error condition, it returns the control to the porting instruction, thereby re-executing it. That is, if the handler is able to cope up with the error condition, that it returns, or then it returns the control to the next instruction, or it controls the return to the next part, that is the next instruction. Then this is a classic example that is given of the fault is the page fault exception. This is a classic example which occurs when an instruction reference or references a virtual address whose corresponding physical page is not resident in the memory and must therefore be retrieved from the disk. So this is the best example, that is if the page fault occurs, if the page fault exception occurs. So there is an instruction reference of virtual address where the physical address, physical page is not resident in the memory and must therefore be retrieved from the disk. A page is a continuous block that is of typically of 4 KB of the virtual memory. So this is this paragraph says that fault occurs, then the control passes to the next part, that is your page handler, then fault handler, sorry, not page handler, then fault handler takes the fault and passes the control to the next instruction. If it will be able to cope up or execute or rectify the fault, then it's okay. Otherwise, the instruction will not be executed by the CPU. So this is the current instruction, creates or causes a fault. Control passes to the handler, fault handler return. So these are the example. That is, first of all, there is a current instruction that causes the fault. Then control pass to the handler. Third point says fault handler runs, then there is a abort condition, then handler either re-executes current instruction or aborts. So it depends on the handler that either it will re-execute, it will define, or it will re-execute the current instruction or abort the current instruction. Then next is your abort, that is the last part of the exception, that is also synchronous in nature, that results from the unrecoverable fault error. So this results from the unrecoverable, that is unrecoverable, that is not recovered. Fatal errors. Fatal error means that is an error that is not recovered. Typically hardware caused or hardware errors such as parity errors that occurs when dynamic RAM or static RAM are corrupted. So these are the errors that occurs when the hardware fails, or the parity bit fails, or the parity error fails, that occurs when the dynamic RAM or the static RAM bits are corrected or corrupted. So if there is a corrupted bit, that is a dynamic RAM, or directly the R bit or R RAM, memory RAM are corrupted, then in that condition abort occur or abort arises. Then abort handler never return the control to the application program. As we have studied all the conditions, control passes to the next instruction. But here the control does not pass to the next instruction. As we have seen in figure 8, the handler returns control to the abort routine that terminates the application program. This is the figure. There is a fatal error or hardware error arises. Control passes to the handler directly. Then abort handle runs. Handler returns to the abort routine. That is there is no provision for returning to the application program. No, it only aborts the condition, aborts the instruction, so that instruction will finish. So these are the errors that is not in use, or that is not in our hand to re-execute the instruction. There is no method to cope up with these types of recover with these types of error. That's why these are known as unrecoverable fatal errors. Next is your exceptions in the Linux or the IA32 system. Let's take a quick review about for the slides, what is covered in the slides. So exceptions are of the type reset, interrupt, or the exceptions. What are the terminology that is used? This is the same exception, that is any unconditional or any condition that is except or that is beyond the normal, that is your condition that cause the processor to escape from the normal control flow. That is if the processor executes except that the or out of the normal control flow, that is known as the exception to a predefined location. Then these are the types of the exceptions, that is reset, that is external, interrupt also external, exception is internal, software interrupted is internal. These are the types. These are the reset types, that is external, puts the processor into a known, that is initial state, and jump to the reset vector address. Then next category is your interrupt, that is also a part of the external, that saves the current program counter and status register in the spatial registers. Then it jump to the interrupt vector address. So these are the categories that jump to the next vector address, that is a jump to the interrupt vector address. Then next is exception, that is internally or that is internal, that is associated with the some instruction, example dividing by zeros. This saves the current program counter and status register in the spatial register. And then jump to the exception vector address. So this jump to the exception vector address. Then next is your software interrupt, that is the next category of the exception, that is internal, that is associated with the special function, special instruction known as the software interrupt, that is used to call the system function, that is used to support the debugging hardware or software. These are the multiple categories that is used when you are using the system. Then this is the diagram that shows the interrupt and the reset. This is the processor core. This is the reset condition. This is the interrupt. There is the interrupt controller. Then various interrupt sources. So these are the various interrupt sources, 1, 2, and so on till more than one interrupt. Then there is a processor core, that is a reset condition. Then at last there is an interrupt that occurs. So these are the two types of exception, that is interrupt and the traps. Interrupt that caused by the external events and traps that are internal events. So these are caused by the external event, as we studied. External events means network, keyboard, disk, page fault, virtual memory. These are asynchronous, that may be handled between the instructions, and they are simply suspend and resume user programs. So these are the external method that is used. One is your traps, that is caused by the internal events, or that is a part of the, or that is a simplification of the also or your assumption of the internal event, that is either exception condition, that is overflow, undefined instructions, hardware malfunctioning. Usually synchronous to the program execution, that is these are the synchronous to the program execution. The condition must be remedied by the handler. Instruction may be retired or retried or simulated, and program continued or program may be aborted. So these are the instructions that is used on that may be retried and simulated to the program. Then next topic is your exceptions in the Linux IA32 system. That is, what are the exceptions that is available in the IA32 or Linux system. To help make things more concrete, let's look at some of the exceptions defined for the IA32 system. There are up to 256 different exception types. That is, there are 26 types of instructions, or 256 type of instruction that is used for the IA32 systems. Number in the range from the 0 to the 31 correspond to the exception that are defined by the Intel architect, and that are identical or thus are identical for any IA32 systems. Numbers in the range ranges from the 32 to the 255 because the maximum is 256. So it range for the number range from the 32 bit to the 255 correspond to the interrupt and trap that are defined by the operating system. Figure 9 shows a few examples. These are the examples of the exceptions in IA32. That is exception number 0. This is the description that is divided by 0. So if they is divided by 0, so that is also exception that is a part of the IA32. 13, general protection fault, that is also a fault. 14, page fault. 18, machine check. 32 to 127, that is OS defined exception, that is either interrupt or the trap. Then there is a system call, that is also a trap. Then OS defined exception, that is also a trap or the interrupt. That is of 129 to 255. So these are the categories of the exception number that start with the 0 and end with the 255. So there are total 256 exceptions that is available in the IA32 systems. Then next is your Linux IA32 page faults and the IA32 faults and the aborts. So these are the categories of the faults and the abort that is used in the IA32 systems. One is your divide error, that is divided by 0, that is we have studied. The general protection fault, that is the infamous general protection fault that occurs for many reasons, usually because of program reference and undefined area of the virtual memory. So if there is an area that is not defined, that is known as the undefined virtual area, that is also a category of the general protection fault. Then next is your page fault, that is an example of an exception where the faulting instruction is restarted. Then the handler maps the appropriate page of the physical memory on disk into a page of the virtual memory, thus restarts the faulting instruction. Then next is your machine check, that is also a category of the fault. These are the multiple popular system calls in the Linux or the IA32 system. One is exit, one is fork, read, write, open, close, wait, execute, else, get PID, alarm, pause, kill, signal. Then these are the system calls that is available. So these are the system calls that is available, that is IA32 system calls. This is the syntax or the example. System calls are provided on the IA32 systems via trapping instruction known as int_n, where n can be a index of the any of the 256 entries in the IA32 exception table. Historically, system calls are provided through the exception, that is 128 exceptions. C programs can invoke any system call directly by using the syscall function. However, this is rarely necessary in the practice. The standard C library provides a set of convenient wrapper functions for most system calls. So these provides some predefined system that are system level function that are used interchangeably by the function to the function. So these are the 10 or these are the multiple categories of the system call that is available in the IA32 or the Linux system. This is the example that shows is the familiar hello program, that is int main write 1 hello world 13, that is writing the code to the or writing the part to the next instruction, that is at 13, that is the hello world. This is the next example, that is section is used for the data, then string hello world, then string end equal length, string end equals to string. Then next is your processes, that is what is a process. So let's take a quick break, that is 5 to 10 minutes break, then come back, then start with the topic that is your processes. So let's take 5 to 10 minutes break. Now let's start with the next topic, that is your processes. So what is a process? That is any program in execution is known as the process. So that is the processes. Exceptions are the basic building blocks that allows the operating system, that allows the OS to provide the notion of a process. What is the notion? That provides the notation of a process, one of the most profound and successful ideas in computer science. So these are the basic building blocks that is useful for the operating system to provide the notion of a process. When we run a program on a modern system, we are presenting with the illusion that our program is only one currently running in the system. That is, whenever we are accessing or whenever we are using the system, we are representing, or we are able, or we think that that is our only program that is currently executing in the system. But that's not true. But our program appears to have exclusive use of both the processor and the memory. That is, our program uses both the concept, both the method, both the technique, that is the processor, that is the CPU, and the memory. The processor appears to execute the instruction in our program. That is the processor that appears to execute the instructions one after the another without the interruption. That is, the processor is able to execute the instruction one after the another without any interruption. Finally, the code and the data of our program appears to be the only object in the system memory. These illusions are provided to us by a notion of a process. The classic definition of a process is that it is an instance of a program in execution. As I told you, it is an instance, means it is an example of a program in execution. So whenever there is a program that is in execution, that is known as the process. So if I'm saying that I'm executing the program, that is a program in the execution. That is, whenever there is a program that execution stage, that is a program, or that is a process. So any program that is in execution is known as the process. Each program in the system runs in the context of some process. That is, every program in the system runs in for some process. That is, every program has an instance of the program in execution. Each time a user runs a program by typing the name of the executable object file to the shell creates a new process and then runs the executable object file in the context of the new process. So every time whenever a user runs the program by typing the name of the relocatable or executable object, then the shell creates a new process and runs the executable file in the new process only. So every time OS runs the program, then a new process will be executed, new process will be created, that is the program in the execution. A detailed discussion of how operating system implemented processes is beyond our scope. That is a so lengthy process that is not in our hand, that is to discuss how how computer system implement the scenarios. That is beyond our scope. Instead, we will focus on the key abstraction that a processor provides the application, or provides to the application. That is, these are the key expression that is provided by the processor to the application. First one is an independent logical control flow. Independent logical control flow means there is a control flow that is not dependent on one another. That is your independent logical control flow that provides the illusion that our program has exclusive use of the processor. That provides an example of our program that provides an exclusive use of the processor. Then the next focus is that private address space that provides the illusion that our program has exclusive use of the memory system. So these are the two methods. These are the expression that is one is your independent global logical control flow. Another one is your private address space that provides the illusion that our program has an exclusive use of the independent use of the memory system. That is your private address space. Now let's see these abstraction, that is, let's see these topics in detail. One is logical control flow. So let's also see some PPTs. What is a process? First of all, definition. That is an instance of a running program. Instance means example of a running program. One of the most profound ideas in the computer system. Not the same as the program or the processor. That is, a process is not same as of the program or the processor, but that is a different, that is any program is in execution is known as the process. Processor provides each program with two abstractions. As I told you, one is logical control flow, one is private address space. How these illusions maintain, that is how these topics maintain, how these methods maintain, by using the concept, by using the multitasking, that is process execution interleaved. One is address space is managed by the virtual memory. So the logical flow is maintained by the multitasking, and the address flow or the address space is managed by the virtual memory system. Then this is the logical control flow, that is every process or the each process has its own logical control flow, that is process A, process B and the process T, and this is the time that starts from the top and ends with the lowest. And next slide says what is a concurrent process, that is your combined process. What is a concurrent process? So whenever there are two processes, that is two processes run concurrently, that is at the same time, that is known as the concurrent process. If their flow overlap in time, that is known as the concurrent process. Otherwise they are sequential. If for example two processes are executing at the same time and they overlap their time, that is known as the concurrent processes. And if there are four processes, their execution time is different, that is known as the sequential processes, that is not concurrent process. Example includes, these are the concurrent, that is A and B, A and C. So this is A and B and this is A and C. Then B and C, this is a sequential, that is your B and C. Next, user view of the concurrent processes, that is what is the user view, how user views the concurrent processes. That is control flow for the concurrent process are physically disjoint in time. How it will be physically disjoint? That is physically separate from one another process, that is known as the physically disjoint process. However, we can think of the concurrent processes are running in parallel with each other, that is concurrent processes are running in parallel with each other with one of the more processes, that is your concurrent process. That is a process that divides into different categories, that is process A, process B and the process C. So these are the concurrent processes that is available that runs in the parallel with each other. Then next concept is that what is a context switching? So this says whenever there is a process, that is the processes are managed by a shared chunk of operating system code known as the kernel. So processes are managed by, controlled by a shared chunk, that is a shared category of operating system code that is known as the kernel. Kernel is not a separate process but rather runs as a part of the user process. So this is also a process, but that is not a separate process but runs as a part of the user process only, that is your kernel. So processes are managed by a shared chunk of operating system that is known as the kernel. Next point says control flow passes from one process to another via a context switch. So whenever there is a control flow pass that is passes from one flow or one part to the or one process to the another process, that is how it will be managed or how will it will pass the control, that is passing the control by using the context switch. So this is the context switching that is used to control or that is used to pass the flow control from one place to the another place, that is process A, process B. This is process A, then process B, then process B to A, then A to A. This is user code, this is the kernel code, then user code, kernel code, user code. Then next is your private address spaces. What is a private address space? Each process has its own private address space. That is, every process has its own private address space that it will be used. That is your private address space. This is the example, that is your OFF. Then memory invisible to the user code. That is, memory is not visible, that is invisible. Then ESP, that is a stack pointer. Then there is a break, there is a time gap. Then loaded from the executable file. Then there is a runtime heap, read-write management, segment, read-only segment, and there is also unused buffer. So this is a private address space. Then next is system call, that is a programming hint that always checks the result of a system call, that always checks the result, that always gives the result of a system call, or -1 on the error. That is, if there is an any error, that is system call is used for controlling the flow, and if there is any error, that is denoted by the -1. Then one of the new method, or one of the function that is used is strerror. That is, your error number tells the error number. What is the error number, and what is the scenario where error came? This is the example. If PID, that is your process ID, equals to fork, that is if process ID equals to fork, or using the fork function, and that is greater than 0, not greater than, yeah, that is greater than or less than 0, then fprintf, that is printing the std error, that is printing the error, fork error std or str error. That is using the function, it calls the function and then exit 0. So this is the function, how system call returns the error. This is the next example, that is Unix error. This is the code, then error message. This is the code that is given. Same example is used. This is again the same example. Then what is a fork? That is used to create the new process. Now int fork void, that is used to create a new process, that is your child process, that is identical to the calling process, that is your parent process. So fork function is used to provide or to create a new process, that is a child process, that is very similar to the parent process, that is it inherit all the commands of the parent process, and returns 0 to the child process. Then it returns child PID to the parent process. That is this is the fork, or the responsibility of the fork. That is, it returns the 0 to the child process. It returns the child PID to the parent process. Then next is your example, that is fork is interesting and often consuming because it is called once but returns twice. That is, it is called only once but it returns twice. That is, if fork equals to 0, that is, if fork is equals to 0, that is, if then printf hello from the child, otherwise, that is else hello from the parent. This is the example that is used for creating the new process. Then this is the example, fork example. Then these are the key points, that is your parent and the child both run the same code. That is the difference between the parent from the child by the return value fork. Then start with the same state but each have a private copy. Then start with the same level but each have a different copy of the private copy. That includes shared output file description, relative ordering of their print statement undefined. This is the example. So these are the possible outcomes that is available. Parent has x equals to 0, buy from with x equals to 0, child has x equals to 0, buy from with x equals to 0. So this is the example of this one. That is, first of all, using the function, that is fork1, then declaring one variable, that is x, and initializes the variable to the 1. That is, first of all, declare the function as well as initializing the variable or initializing the value but the x. Then PID equals to fork, that is using the fork function, call the fork function and store the result in the PID. Then uses a condition, that is if PID equals to 0, that is if PID, that is your process ID, equals to 0, then print the child has x equals to plus x. That is, first of all, incrementing the value of x and then print the value of x. Else print the value of parent, that is parent has x equals to minus x. That is, first of all, decrementing the value and then print the value by using the printf statement. At last, there is a printf, that is a buy from the process, that is executed at every time by using the x value. So in the same way, the parent has a x equals to 0 first of all, by with x equals to 0, child have a 2, then by from with x equals to 0. Both child and the parent can continue the forking. So this can continue the forking, that is printf, LO line 0, fork, printf, L1 that is line 1, fork, then printf by. That is the next example, that is your fork 2. This is shows L0, L1 by. Both parent and child can continue the forking. Same example. Void forks, that is more than one forks, L0, L1, L2 by. At every time fork function is. Hello, hello, hello.
I can hear you.
Okay, thanks a lot. So this diagram shows different processes, that is process A, process B, and the process C. So in this, the execution of three logical flows is interleaved. Process A runs for a while, that it runs for a while, then it waits for a process B, that is followed by the process B, which runs to the completion. Then process C runs for a while, that is process C runs for a while, that is followed by the A. This is followed by the A that runs to the completion. Finally, C is able to run to the completion. The main point or the key points is that processes that takes using the processor, that is processes that take turns using the processor. Each process executes a portion of the flow and then it is preempted, that is temporary suspended, that is known as the preempted, while other processes that takes turn. So this shows that one process is executing, that is followed by the another process, the next process is executing, that is followed by the next process. Finally, one process executes the or finishes or runs to the completion. Then the only evidence of contrary is that if we were to precisely measure the elapsed time of each instruction, that is how much time it takes, we will notice that the CPU appears to periodically stall between the execution of some instruction in the program. So it is not able to cope up with the program, that is how one program or one process is executing and what is the time gap between the different processes. Then next part is your concurrent flows. So till now we have studied about the logical control flow, that is category of the processes, how CPU handle the processes. Then next is your concurrent flow, that is what is the concurrent flow and how it will be used. This says logical flow takes many more forms in computer system. Exception handlers, processes, signal handlers, threads, Java processes are all examples of the logical flow. So these are the all examples of the logical flow, that is how logical flow will be maintained. A logical flow whose execution overlap in time with another flow is known as the concurrent flow. So any logical flow whose execution or whose operation overlap in time with another flow, that is process A overlap with another process, that is known as the concurrent flow, and the two flows are said to be run concurrently. More precisely, that is, for example, if we are using two processes, that is flow X and the flow Y are concurrent with respect to each other, that is these are common with respect to each other, for example, then each other if and only if X begins after Y begins. That is, if they are concurrent execution, that can be possible if the X begins, then after the Y begins. That is, once the Y finishes the execution, then X begins. That is, and before Y finishes, Y begins after X begins, and before X finishes. So this is the example, that is X begins after Y begins, and the before B finishes, and Y begins after X begins, and before X finishes. That is, if one process is executing, that is executing only the current instruction, only current process. For example, in figure 12, processes A and B runs concurrently, as do A and C. So this is figure 12, that is process A and B runs concurrently as the process B and C. So that are concurrent flows, that more than one process are concurrently executing at the same time. That is, A and B are concurrent, so as do A and C. On the other hand, B and C do not run concurrently. So these are the two processes that are not run concurrently, but A and B and the A and C are running concurrently. Why? A, B, A, C. This is AC, this is AB, not BC. On the other hand, B and C do not run concurrently, because the last instruction of B executes before the first instruction, the C. That is, they are not concurrently executed with each other. So there is no overlapping in the time between these instructions. The general phenomena of the multiple flows executing concurrently is known as the concurrency. That is, whenever there are more than one process that is executing the command, that is known as the concurrency. The notion of a process taking turns with another process is also known as the multitasking. So these are the concepts that is used in the concurrent flow, that is concurrency, multitasking. Each time period that a process executes a portion of its flow is known as the time slice. So these are the time periods, or each time period that a process executes a portion of the flow, portion of its flow is known as the time slice. Therefore, thus multitasking is also referred to as time slicing, that dividing the time into multiple processes, multiple tasks, that is known as a multitasking. For example, the flow of process A consists of the two time slice, that is, it divides into two time slice. This is one time slice, this is one time slice. In the same way, process C is also divided into two time slice, that is, process C is executing in two time slice, that is decided by the operating system. Notice that the idea of concurrent flow is independent of the number of processor cores or computer that the flows are running on. That is, it is independent of the number of processor or the core that is using or that is flowing on the computer. If two flows overlap in time, that is, if there are two flows that overlap in time, and then they are known as the concurrent, even if they are running on the same processor. That is, if two flows overlap with each other, if there is only, for example, if there is only one CPU, that if there is only one CPU or more than one CPU, in any condition they are known as the concurrent processes. However, we will sometimes find it useful to identify a proper subset of concurrent methods or concurrent flows that are known as the parallel flow. If two flows are running concurrently on different processor cores or computer, then we will say that they are parallel flows, or they are running in the parallel and have parallel execution. So whenever there are two flows that is running concurrently, they are known as the concurrent process, or the parallel flow, or the parallel execution, or running in execution. This is example. Consider three processes with the following starting and the ending point, that is 0, 2, 1, 4, 3, 5. For each pair indicates whether they run concurrently or not. This is concurrent. This is A, B. That is, A and B are concurrent. Yes. Why? Starting time is 0. Here 1, then 2. So it lies between, one lies between the 0 and the 2. So they are concurrent process. In the same way, A, C. That is 0, 2. 1, 4, 3, 5. But they are not concurrent process because they are executing one after the another. In the same way, B, C are concurrent process. Then next part is your private address space. So what is a private address space? This is also a category of the process that is executing or an operating system uses. As I told you, private address space is the space that is the outcome of the 2 power n possible outcome or possible addresses. That is, if process divide each program with the illusion that it has an exclusive use of the system's address space. On a machine with n-bit addresses, the address space is the set of the 2 power n possible addresses that start with the 0, 1 and 2 power n minus 1. A process provides each program with its own private address space. So every process provides each method with its own private address space. This space is private in the sense that a byte of the memory associated with the particular address cannot be read or written by any other process. So this space is private, that is in the sense that byte of the memory in general cannot be written by the another process. So if one byte is available for one memory or for one process, that cannot be used by another memory for the same memory or another process by the using the same memory. Although the content of the memory associated with private address space is different in. Then next is your user and the kernel mode. As I told you, In order for the operating system, kernel is provided an all airtight process abstraction that is used to provide the system execution in time. The processor must provide some mechanism that restricts the instruction that an application can execute, as well as the portion of the address space that it can access. These are the two modes available. This is the diagram, as I told you, with the help of PPTs. The same example. Next is your context switch that I also told you. What is a switching? That is movement from one part to the another part. This is the operating system kernel implements multitasking, that is more than one task is executing at the same time using a high level form of exceptional control flow known as the context switch. This mechanism is built on the top of the low level or lower level exception mechanism that we will discuss in the section number 1. The kernel maintains a context for each process. That is, it is a responsibility of the kernel to maintain for each process or to maintain a context for the each process or each and every process. It consists of the values of the objects such as general purpose register, floating point register. So there are different categories of the register that is used. That is general purpose register, control flow registers, process table, file table that contains the information about the processes. Then a scheduler is also used that controls the flow, that controls the context switch. This is the example that we have discussed with the help of PPTs. Next is your system call error handling. This is the same example as I told you with the help of the slide, that is how to adopt with the error, that is the system call error handling. The same example, that is less than 0. The printf error condition, that is a function that is used, is str error function returns a text string that describes the error associated with a particular value of error number. This is the same example that we will discuss with the help of PPTs. Next is your process control. That will be discussed after or in the next class. Yeah, one important thing is that there will be no class for the tomorrow due to the elections in the India, that is in Gurgaon. Now the class is on day after tomorrow, that is on Thursday. The same timing will be same, but there is no class for the tomorrow. Now, if you have any doubts, then please text the doubt. That's all for today's session. Now, I'm going to continue with your next topic, that is your process control in the next or the day after tomorrow, that is in the Thursday's class. Now, if you have any doubts, then please text the doubt and I will answer your doubts. So that's all for today's session. Thank you so much everyone for listening me.